This is Unit 10, Lesson 3. This lesson's on inverse functions. As we're going through, there's going to be parts that I'm kind of just skipping over, so don't freak out and be like, oh my god, there's nothing there. Yep, that's on purpose. Okay, so inverses. What does the inverse mean to you? Well, to me, it means opposite. Okay, and we're going to be talking about that a lot. Okay, so we're going to be finding opposite functions. So we're going to take a look at how to find inverses graphically, algebraically, how to prove if things are inverses by using composition, and how to determine something if inverses are truly functions, and all that good stuff. So it's important to know that an inverse function undoes another function. It literally undoes everything. Does that word make sense? Yeah, okay. So we're going to talk about that. All right, now something you need to know is that for a function, so f of x, okay, so that's function notation, if we have a point xy, okay, so that's a point on the function, for its inverse, and something I want you to know, inverse is denoted as f to the negative first. That's not saying like, you don't treat that like an exponent. It's not 1 over f. That just means it's an inverse. So for the inverse, it's going to be the point y comma x. So one big relationship between functions and their inverse functions is the fact that the domain and the range just switch places. Domain and range switch. All right, so this first example that's talking about people, it's kind of just a silly way to illustrate that. If all those people in the domain, for the inverse function, they would be part of the range, and vice versa. When I talk about it in terms of points, okay, if I'm saying here's a function, now first of all, we know it's a function a because I told you, hey, this is a function. We also know because if you look at all your x values, they don't repeat. So remember, each x value has to be paired up with one and only one y value in order to make it a function. Yay, that works. Okay, so if I'm asking you for the inverse, I'm asking you, and now this is just a bunch of points, switch your domain and your range, meaning switch your x's and your y's. So we can go through and we can just switch the coordinates of the points. So negative 327 on the original function is going to be 27, negative 3 on the inverse. All right, since it's going to take me a minute, I'm just going to pause the video to switch those points. I'll be right back. All right, so there my points are. So is the inverse a function? Okay, well, let's take a look. Do my x's repeat? No, so it is also a function. All right, now let's start our next one. It's a function. None of my x's repeat. For my inverse, if I just flip them, I move to the board, so it'll be a little bit easier and a little bit more legible. So I'm just flipping my x's and y's. Is the inverse a function? No, it is not. I have the x value 9 twice, I have the x value 4 twice, and 1 is twice, so it's not. So is the inverse of a function always a function? No, okay? So in that case, if I'm asking you to find the inverse, if it's a function, it's the inverse function. If it's not, it's the inverse relation, okay? Because it's still an inverse, the opposite, just not a function. Why does that matter? All right, because we're going to talk about one-to-one functions now. So when the inverse of a function is a function, then we call it one-to-one. It's kind of like a special group, a secret society that you have to be part of. So a function is one-to-one if and only if its inverse is a function. In one-to-one functions, not only does every input or every x value have one and only one output, but vice versa. So you can tell from looking at the original points, like if I looked up here, not only should my x's not repeat, but neither should my y's. If that's the case where neither repeat, then it's a one-to-one. But if looking at it, I see that, hey, some of the y's repeat, so even though the original is a function, my inverse is not going to be. Okay, so you can tell from the original graph whether it's going to be one-to-one, meaning whether if the original and its inverse are functions. All right, and you can also tell, remember back in the day when you did the vertical line test, you drew vertical lines through your graph to determine if it's a function. So same thing, but we can also draw a horizontal line to determine if the inverse will be a function. All right, so looking at example A, it passes my vertical line test and it passes my horizontal. I know it kind of looks right here, but that's just a bad picture. It's just a cubic. It's not flattening out there. So since it passes both tests, it is one-to-one, which means my my inverse is a function. In part B, it passes my vertical, but it does not pass my horizontal line test. So it's not one-to-one. The inverse would not be a function. Ooh, I got an email. All right, in C, it passes the vertical line, but does not pass the horizontal, so it is not one-to-one. All right, Let's figure out how we write the equations of inverses now. All right, so let's just take this first example. F of x equals 2x, all right, or y equals 2x. So let's just think about what's going on here, and then I'll show you a foolproof method that will work every time. So here are some points, 2, 4, 3, 6, 4, 8, 5, 10. How did you get that? Well, I simply took 2 and plugged it in and did math and got 4. I plugged in 3 and got 6, okay? So those are just points on that function. Now, if you remember, I told you the domain and the range switched, so the x's and y switches, so here's would be the points on the inverse. So what's happening there? The x is double the y, all right? Or y is 1/2 of x. So here's my inverse equation. Now, anytime you're doing, if you have a line, rephrase, majority of the time when you have two lines, they're both going to be functions. There's only one situation where it wouldn't be, if the original is a function. If you have a horizontal line and you find its inverse is vertical. So in that case, the inverse would not be a function. But any other time you have a line, its inverse will be a line in their functions, okay? Except for verticals and horizontals. So the inverse of 3x minus 1. So let me show you the method that works every time. Okay, you can think your way through it. Or, first things first, replace f of x with y. So y equals 3x minus 1. Then I'm going to go ahead and I'm going to switch my x and my y. Now I need to solve for my new y, so I'm going to undo everything. So if you remember, we said the inverses undo, or an inverse undoes the original function. So we're moving everything over in reverse order of operations. Now if I have a denominator first, I'm going to have to get rid of that. Here I don't, so the opposite of subtracting 1 is adding 1. The opposite of multiplying by 3 is dividing by 3. All right, so there's my inverse function. All right, you can see another one down below. If I give you the original function is 2x squared plus 7, and I'm asking you to find the inverse, okay? We're going to go ahead and we are going to replace x and y. So I've got 2y squared plus 7 equals x. Subtract 7, so 2y squared equals x minus 7. Divide by 2. Take the square root. Anytime you're taking the square root by hand, we're going to put that plus minus. We're going to talk more about this next time, the whole quadratic to square root things, because there are some domain and range restrictions we'll have to consider, but we don't need to worry about that right now. Okay, just know, oh, that's a 2 down there. Knowing, all right, in order for my u to really have an inverse, I need both a positive and negative square root. All right, so now we're going to talk about how to prove if two functions are actually inverses using compositions. Okay, so if I give you two equations and I say, hey, are they inverses? You could just take one and physically find the inverse equation by hand and then see if it matches, but we do need to be able to prove using inverse or compositions. So what this says is if you take one function and substitute it into the x value of the other, it needs to equal x, and vice versa in order for it to be true inverses. So they both have to simplify out to x. Okay, so if I use these two examples, if I do f of g of x, I'm taking g, plugging it into f. So I'm doing 3 times 1/3 x. When I simplify that out, I get x. That's good. That's what I want. Now if I go the other way, I do g of f of x. I'm doing 1/3 times 3x. Same thing. So since they both equal x, it's telling me, hey, those are inverses. If you get anything else besides x, like even if it's just a negative x, they are not inverses. They both have to simplify to x. So if one does but the other one doesn't, they are not inverses. All right, our examples down here. So we're going to do h of g of x and g of h. All right, so I'm taking g first, plugging it in over here. So I'm doing x, sorry, replacing that, jk. So I'm doing the cube root of x to the 3rd power. Cubing and cube rooting undo each other. I'm left with x. Yay. When I do it the other way, I have the cube root of x cubed. Same thing. They undo each other. Yay. So some of them you can tell just by looking at it, but we do still need to practice to make sure we can do it. In my next example, it says h of g of x equals x and g of h of x equals x. So it's just telling me, hey, if you did the compositions, you got x. So what does that mean? All right, they are inverses. All right, we should have said yes over here as well. Sorry. All right, and then in my next example, excuse me, I apologize. Same thing, we're going to do f of g of x, and then we're going to do g of f of x. Doesn't matter which way you go first. Let me switch colors here. Okay, so so this into here first. So I've got 1/5 times 5x plus 5 minus 1. So I have x plus 1 minus 1. So that one worked out. All right, so now I got to make sure it's going the other direction. Don't assume. So now I'm going to do 5 times 1/5 x minus 1 plus 5 equals x minus 5 plus 5 gives me x. Check. All right, so yes, those two are inverses. Okay, so we can use composition to determine if two functions are truly inverses. All right, now we're going to talk about graphs. So I'm going to do some more with this next class, okay? So find the inverse of the function, then graph it. All right, so if I have y equals x squared, the inverse, so I'm going to switch x and y and take the square root, is going to be plus and minus x. Okay, because I need to make my u whatever. So my original function is x squared. So start at the middle, up 1 over 1, up 3. I'm expecting that we know the pattern by now. Here is my quadratic. Now, an inverse should look the same, just kind of on its side. So if I graph the positive square root, it looks like this. And the negative just goes down. So something that you need to know is that graphs of inverses reflect. And they reflect over the line y equals x. They reflect over the axis of symmetry, which is this line right here. It has a slope of 1 and y-intercept of 0. So let me draw the original one. And I kind of freehanded it up, but you get the idea. If I were to fold that paper on that red line, they should match up. Now for a quadratic, my original function is an inverse, but my original function is a function, but my inverse is not, because the inverse itself will not pass a vertical line test. Looking at the original function, I can tell because it wouldn't pass a horizontal line test. That one tells me if my inverse is a function or not. So we're going to do this more next class, talking about restricting. Okay, so it says sometimes we restrict the domain and or range so that the inverse is truly a function. In the above example, how can we restrict the domains to make it an inverse? Okay, so I could say to you, hey, let's go ahead and only look at half of it. So if we're looking at for when x is greater than or equal to 0, that's this side right here. That did not work out. So which part is that going to reflect down here? It's going to be this part. Okay, because those are where the x values are greater than or equal to 0. Because remember that when you your x's and your y's switch. So my original graph, x is greater than or equal to 0 and y is greater than or equal to 0. So the inverse should be, well, it ends up being the same. Now let me get a different color here, the purple. Now I'm going to do bright yellow, just make it very different. Okay, so if I look at this graph, just that part, my domain would be x is less than or equal to 0 and y is greater than or equal to 0. The inverse should have those flipped. So my inverse will end up being this part down here. These two yellows match up. Okay, the yellows from over there. Because the domain here, if you just look at this second yellow part over here, this part, the domain is x is greater than 0, but y is less than or equal to 0, which is the flip-flop of the original domain and range. Okay, so sometimes we can restrict it because now if I'm just looking at part of the quadratic, its inverse is truly a function because it's just one part of the square root. And we are going to do more with the restrictions next class. What I want you to be able to get out of this lesson is how to determine if two inverses are if two equations are inverses using composition, how to write the inverse equation algebraically by switching your x's and y's and solving for y, knowing that a graph is a reflection over y equals x, and knowing that our domain and our range is switch. All right, and that is all that we are going to do for now.